Okay, everybody, last lesson for the week. And today's lesson pretty straightforward. We're going to be using the table of relative strengths. And one of the things about the acid-base unit is it has a lot of parallels to the redox unit. So you had a table of relative strengths for redox, and we have a similar table of relative strengths for acids and bases. So today you guys are going to learn the rules for predicting percent reaction. And then we're going to be using the 5-step method for acids and bases, just like we did for redox reactions. So some similarities today, and then we are done for the week because you have, what do you guys have again tomorrow? I keep forgetting right, graduation for our grade 12s. Okay, rules for predicting the percent reaction for acid-base reactions. So the rules are pretty simple. Any strong acid will react quantitatively. So we say greater than 99% with any base. It doesn't matter. So if we're looking at our table of relative strengths and we have our big 6 strong acids, they will react with any base greater than 99%. So it's sort of like that redox table where we said if the oxidizing agent is above the reducing agent, it's spontaneous. Well, here, if it's a strong acid, it's greater than 99%. So it's a little more refined than just saying spontaneous. We actually give the percentage of reaction, okay? If it's a strong base, same thing. Any acid, doesn't matter how strong or weak, any acid will react with a strong base greater than 99%. So we have 2 quantitative reactions. Strong acid, strong base. They're both greater than 99% with any partner. Weak acids and weak bases. These are the tricky ones. If you could call them tricky, they're just different. So the rule is, and this is more like the table of relative strengths for redox, if the weak acid is above the weak base, we say greater than 50%. If the weak acid is below the weak base, we say less than 50%. So here is a weak base. And here is a weak acid. How would we classify that reaction? Weak acid is below the weak base, less than 50%. And if we had this weak acid with this weak base, the weak acid is above the weak base, we would say greater than 50%. So we have greater than 99, greater than 50, less than 50. Those are our 3 choices. So we're going to try these out on some reactions. We'll use this table of relative strengths. It's not quite the same as the one in your data book. Okay, so first one we're going to look up is acetic acid in water, vinegar in water. So acetic acid is right here as an acid, and there's water. So we have a weak acid and a weak base. Weak acid is below the weak base, so we are going to put down less than 50%. Okay, strong acid with water. We don't even have to look it up. As soon as we see it's a strong acid, we're done. Greater than 99%. Okay, CH3COO minus and water. This is a minus, so it's probably a base. We'll go look it up. CH3COO minus and water. Okay, here it is. CH3COO minus. It's in the conjugate base column, and it's a weak base. And water is the weakest acid right here. So we have this weak acid below a weak base, less than 50%. Oh, isn't this easy? Less than 50%. Okay. H3PO4 and NH3. H3PO4 and NH3. Let's clean this up a little bit. Whoops, H3PO4 and NH3. Okay, H3PO4, NH3. NH3 is right here. And H3PO4 is right here. Okay, so this is a weak acid. The cutoff is right there for the strong acid. So we have a weak acid and we have a weak base because the cutoff for strong bases is right there. So what are we putting when the weak acid is above the weak base? Greater than 50%. Okay, another weak acid, another weak base, HCO3 minus and SO3 2 minus. SO3 2 minus is, where is it? Right there. Switch colors. And was that HCO3 minus? Yeah, HCO3 minus. Okay. HCO3 minus is right here. So, Olivia, what do you pick? Correct. Less than 50%. Whoops, wrong way. And the last one is a strong acid and a strong base. We don't have to look that up. If either one of them is strong, done. Greater than 99%. And you also notice they're using that arrow to show you that. It's quantitative, greater than 99%. Okay, so there's two more that you could do here if you would like. I'm going to save you some time. That's a strong base. Hydroxide, we're done. Greater than 99%. And that one is a weak acid and a weak base. And when you look it up, you will discover the weak acid is below the weak base. Less than 50. Okay, we've beaten this one to death. Easy peasy. Done. Okay. Now here comes the harder part. 5-step method. So this, let me back up. In Chem 20, Chapter 5, you learned how to identify entities present in solution. We did it a little bit in redox, so we're going to hit it again. You have to be able to look at any compound and know what does it look like in solution. So we don't really worry about solubility rules in this unit. If it's an ionic compound, we break it apart into its ions. So that's easy. We treat them all like they have at least some solubility and we have ions present. So ionics, break them apart. Ionic oxides are interesting and unusual. They break apart. So Na2O or CaO, they will break apart into O2 minus. Now you might be wondering, well, how does O2 minus become hydroxide? O2 minus in water because it's a 2 minus, it is able to pull a proton from water. So if water loses a proton, it turns into OH minus. And if O2 minus gains a proton, it turns into OH minus. So ionic oxides actually make two hydroxides, which make them very good bases. Unusual. So ionic hydroxides and ionic oxides will call it dissociate, and we get those OH minus ions. Okay, strong acids, 100% ionize into hydronium, and we've done that already. Weak acids, because they all react less than 50% in water, and I'll just show you that on this table. So here's water as our base. every single weak acid is below water. So all of them react less than 50%. So if they are reacting less than 50% in water, that means they stay together. HF stays as HF. HSO3 minus is HSO3 minus. So the majority of entities present are the original molecules. They stay together. And you saw that in some of those percent reactions. They were like 3%, 4%, 5% ionize. So the major entity or the most common entity is the molecule, and the same thing with weak bases. They stay together. Whatever you start with is what you finish with. So NH3 is NH3, HCO3 minus is HCO3 minus. So weak stay together, strong ionize 100%, and ionic compounds dissociate them into their ions. So those are the rules for the 5-step method. All right, let's practice it. So what you have to do is when you are given a compound, there's a little bit of a flow chart or a decision tree. You have to look at it and decide whether it's ionic or molecular. If it's molecular, go and look it up. If it's a strong acid, then you 100% ionize. And if it's a weak acid or a weak base, you just leave it. LEAVE. Okay, so that's your moleculars. If they're ionic, dissociate them. And then once you dissociate into its ions, you go and look up the ions. If you see hydroxides, it was a strong base. Check the table. You could have a weak base or a weak acid hidden inside of the ionic compound, and you don't see them until you break it into its ions, and then you go searching. You will discover that in this table, there are lots of ions. What a mess. Holy smokes. Ugh. So I'll just show you some examples. So here's an ion that came from an ionic compound. Here's an ion. Here's an ion. Here's an ion. Ion, ion, ion. So you can see lots of weak acids and weak bases come from ionic compounds. So once you dissociate them, you go searching on that table to see if they are an acid or a base. Okay. So we'll practice a few of these together and you'll get the pattern. List all entities present and then decide, is this thing an acid or a base, strong or weak? HCl, it's molecular. You look it up. It's a strong acid, so it goes 100%. Hydronium and chloride, it's reacting with water. Everything in here is aqueous. I'm not even going to bother writing aqueous to save some time. H3O plus Cl minus, 100%. Okay, molecular compound, you look it up. It's a weak acid, so you just leave it. Done. Barium hydroxide, ionic compound, dissociate it. And then go look up the ions. That one does nothing. This one is a strong base. Na2CO3, ionic, dissociate it. Whoops, 2 Na pluses and a CO3 2 minus. You go searching. That one's a spectator. CO3 2 minus is a weak base. This is in washing soda, in case you're interested. NH4OH, that's tricky. It's an ionic compound made up of NH4 plus and OH minus. You go look on the table and you go, whoa, that's a weak acid and that's a strong base. So ammonium hydroxide has both a weak acid and a strong base. HClO4 is molecular, so you go searching on the table and it's one of the big six. It's a strong acid. So it's 100% hydronium and ClO4 minus. So for example, if it was 3 molar, we now have 3 molar hydronium and 3 molar perchlorate ions. KHS, ionic, dissociated, K plus, HS minus. Oh, I'm not doing aqueous. Go searching. That one's a spectator. HS minus is both a weak acid and a weak base. It's not always listed on both tables, but you would recognize it's a weak acid because it has an H, and it's a weak base because it has a minus. And I honestly don't remember on this table If it's in both columns, let's just take a peek. HS minus. Can I find it amongst the chaos of all my mess? Not seeing it in the conjugate base column. Here it is as a weak acid, and some tables will also have it as a weak base sitting somewhere up there. Okay, back down here. Almost done. Major entities present. LICN, ionic. Whoa, dissociated. Li plus, Cn minus. That one's a spectator ion. It's not in the table. This one is a weak base. H2O2, molecular. Leave it together. Go searching on the table. It's not on the table, so it is neutral. Trick question. Looks like it would be a weak acid, but it's not. It is not found in that column of weak acids. Okay, you can search all day long in here. You will not find H2O2. By the way, there's that Cn minus that we were talking about as a weak base. Oh, here's HS minus in your table as a weak base. It's funny that they have it as a weak base here, but they don't have HS minus as a weak acid. And the table that I showed you had HS minus as a weak acid, not as a weak base. So tables don't have all of the acids and bases in them, right? Just like your redox table didn't have every oxidizing and reducing agent. So it depends on the table you're using. Okay, let's get into the meat and potatoes. So you had to learn two things today: percent reaction and being able to identify all the entities present. And now we're going to cram it all together to properly predict acid-base reactions. And this is the last big part of chapter 16. And this is what we'll be using for pretty much the rest of the chapter is this skill. So let's take a look at it. This is the 5-step method. I'm not going to read it. I'm just going to go through the steps with you as we actually try them out. Okay, so ammonium nitrate fertilizer is produced by the reaction of ammonia with nitric acid. Write a balanced acid-base equation using the 5-step method. Okay, so we're starting out with ammonia and nitric acid. Aqueous, there's solutions. Okay, so now I'm going to be a little more careful with my states. So here's our starting points. They're aqueous, so that means water is present as well. Okay, so step 1, list every entity present. This is molecular, so it stays together. And I'm going to look it up, and it is a weak base. Nitric acid is one of the big 6 strong acids, so that's not how it exists. It does this, 100%. Hydronium and NO3 minus. That's what it really looks like in water. And we know that this is a strong acid, and this one is just a spectator ion. It's super weak. And then we have water, which is a weak acid and a weak base. So 5-step method, I've gone through and listed all entities present. I've classified them as acids or bases. Now we're going to pick the strongest acid and react it with the strongest base. So our strongest acid is a no-brainer. That's H3O plus. And our strongest base is either NH3 or water. So we go searching, strongest base. There's NH3, which is way stronger than water. So NH3 is our strongest base. Now we use Bronsted-Lowry theory. Our acid donates a proton to our base. Oh, we're just putting it all together today. So predict the products. That becomes water, loses a proton, and NH3 becomes NH4 plus. So that's our Bronsted-Lowry acid-base reaction. Step 5, classify. Greater than 99, greater than 50, less than 50. We have a strong acid. We're done. Strong acid means greater than 99%. So that is the 5-step method to give us a proper acid-base reaction when you have nitric acid with ammonia. So it's the hydronium of nitric acid that donates a proton to ammonia, making water and ammonium, and it is a quantitative reaction. If we want, we could put one big single-headed arrow because it's greater than 99%. That, ladies and gentlemen, is the 5-step method. So we will do another problem just to sort of solidify it for you. I think we have 2 more to do, 1, 2, and then we're done. Yay. And then that's it for the week. Okay, spilled drain cleaner is neutralized with vinegar. Spilled drain cleaner is sodium hydroxide solution, aqueous, is neutralized with vinegar or acetic acid, CH3COOH, aqueous. Because they're both aqueous, that means we have water present, and we always list water too because it is also an acid and a base. Okay, write a balanced acid-base equation using 5-step method. This is an ionic compound, so we'll break it apart. Na plus, OH minus. This is molecular, so it stays together. And then water is a molecule, it stays together. Classify them. Na plus is nothing. This one's a strong base. This one's a weak acid. So I can find these on the table. I can look them up on here. There's my, what was I looking up again? CH3COOH, which is right here. Whoops, didn't go up far enough. Okay, what's going on? I missed it. Right there. CH3COOH and hydroxide, which is our strong base, which is way down here at the bottom of the table. I'm just jumping all over the place. Okay, so there's our acetic acid or vinegar, and here's our hydroxide as a strong base. Okay, so strongest base, hydroxide, reacts with our strongest acid, and we only have 2, water and acetic acid, and acetic acid is stronger. Acid donates a proton to the base, so you can predict the products. HOH or H2O and CH3COO minus. And because this one's a strong base, we're done. Classifying is greater than 99% as well. Awesome. 5-step method. Okay, last one. Baking soda, sodium hydrogen carbonate, sprinkled around cat litter box to eliminate the odor caused by ammonia. Write an acid-base reaction and equilibrium position. Cat litter, there's urine in there, which means it's wet, so we're going to throw water in as well. Okay, we already know this is a molecule and it's a weak base. And this is a molecule, weak acid, weak base. This one's ionic. Break it apart. Na plus, HCO3 minus. Okay, Na plus is a spectator ion. It's not on the table of relative strengths as an acid or a base. HCO3 minus is found here as a very weak acid, and it's found there as a weak base. So it's amphoteric. Weak acid and a weak base. Okay, identify our strongest acid, HCO3 minus or water. And it's HCO3 minus. It is stronger than water. And weakest base, we have HCO3 minus and ammonia and water. And the strongest base of those would be the HCO3 minus or the ammonia. Ammonia is only 4 away from hydroxide, so ammonia is the strongest, NH3. Okay, predict the products. So our acid donates to our base. So we get CO3 2 minus and NH4 plus. Percent reaction, HCO3 minus and NH3. So there's NH3. And there is HCO3 minus. So that one is just slightly uphill. The acid is below the base, less than 50%. So we do not get a complete reaction on that one. That is Bronsted-Lowry 5-step method. There is a bunch of questions that you could work on. So there's textbook and study guide, page 366, and I will put the answer key online for this. And I feel like I don't think I'm going to give you guys a quiz this week. I'm just deciding this right now because I think you have enough to do and you've got grad tomorrow. So we'll pick this up on Monday after grad, Tuesday, whatever day we start again. I don't remember. So finish off these questions, and then next week we will talk about some type of a quiz or assessment to make sure that you understand the 3 days of content that we've done this week. Happy graduation, everybody. I hope you have a great day tomorrow, however that unfolds for you. Hopefully the sun is shining, you're with friends and family, and just having a good time. Okay, take care, everybody.